In this video, I want to take a look at the calculation of arc length when I have a curve given in terms of a vector function, or in terms of parametric equations, however you want to think of this. Back in a Calc 2 class, we would have done similar calculations with curves that are described as either y as a function of x or x as a function of y. And we start off in the same way as back in a Calc 2 class. If you got some curve, right, this is a curve in space. It would also work if it were in the plane. I just ignore this last component, but we got this curve in space, and we want to say starting from here at t equals a and ending there at t equals b, I want to know how long that curve is. If I were to take it, pull it straight, don't stretch it, just straighten it out, see how long it is. And in typical Calc 2 fashion, we do this by cutting it up into a bunch of little pieces, finding or estimating the length of each piece, and then adding up all those estimates to get an estimate of the total length. And then you cut it up into a smaller number, into a larger number of pieces so that each piece is smaller, and see what we get. As we do that again and again with more and more pieces, to get better and better approximations. The thing is, each of these little bits of arc can be approximated by a straight line. Now, a straight line segment. Now, in a Calc 2 class, we would have said, oh, there's a dx and a dy. Well, now I'm in space, and that little line segment actually has a dx, a dy, and a dz. So this is down in the xy plane. This is perpendicular this way, and that ds is given by the distance formula in R3, so that that little bit of arc length squared is dx squared plus dy squared plus dz squared. Right. Take the square root to get the actual length. Now, in Calc 2, it looked like this, and we would say, oh, factor out the dx squared, or factor out the dy squared. What I want to do now is I want to say, factor out the dt squared. And you might say, but Will, there's no dt in there. And I would say, over on the side here, I would say, so? I mean, you can take anything here. Here's the 12x plus 24. I'm going to factor a 7 out of that. Say 7? There's no 7s in there. Aha, but there is. Because I would just say 7 times 12x divided by 7 plus 24 divided by 7. I've factored a 7 out by dividing everything in there by 7. So I'm going to look at this thing right here, and I'm going to factor a dt squared out of that. So I have ds squared equals dx squared over dt squared plus dy squared over dt squared plus dz squared over dt squared, all times dt squared. Now I'm going to take the square root of both sides and say that ds is the square root of dx dt squared plus dy dt squared plus dz dt squared, and the square root of dt squared is dt. Notice that this stuff under the parentheses, the dx dt, dy dt, and dz dt, are precisely what you get when you take the derivative of r. So that this calculation right here is actually the length of the derivative vector. And so the total length of the curve is going to be the sum of all the pieces, all of these, length of the derivative vector times dt, all the way from t equals a to t equals b. Add up all of those little bits of arc length to get the total. Okay. This is an interesting formula right here for several reasons, one of which we'll better be able to talk about when we get to the next section, but we'll talk about this curve being a position vector, and the derivative of a position vector will be the velocity vector. And if you look at the length of the velocity vector, you're talking about the speed. And if you take speed times time, well, speed times time is distance. So speed times a little bit of time is a little bit of distance. And if I add up all those little bits of distance, I'm calculating how long the curve is. Okay. Let's do an example. Let's do the standard helix here. So I've got r of t equals cos t sine t t. And I'm going to do just one time around this helix. So t is between 0 and 2 pi. So I'm looking at, what does it start out here on the x-axis? And it goes around once and up here, right? This would continue going around and up like a spring, right? Some people say spiral. It's not a spiral. It's a helix. Spirals are planar. Helixes are not planar. Anyway, look at r prime. The derivative here would be minus sine t cos t 1. The length of that is the square root of sine squared t, the minus becomes plus, cosine squared t plus 1 squared, which is 1. But look at sine squared t plus cosine squared t is 1. So this is the square root of 1 plus 1, which is the square root of 2. So that integral that we're trying to do now, the length of this curve, is going to be the integral from 0 to 2 pi, starting value of t to ending value of t, of this square root of 2 times dt, which I think I can do that one in my head. Square root of 2 times t, evaluated from 0 to 2 pi, which is 2 radical 2 times pi minus 0. Okay. Now I have a way of checking this because I noticed that this curve actually completely lies on a cylinder of radius 1, and if I were to take that cylinder, cut it right there and open it up, it would unroll into a rectangle, and that curve would actually just unroll into a straight line, where the distance around here, the distance around the cylinder would be 2 pi times the radius, but the radius is 1. So that's just 2 pi. And the altitude that I gain here, this altitude, well, z goes from 0 to 2 pi, so that's also 2 pi. So this length right here is, well, that's 2 pi times the square root of 2. It's a 45-45 right triangle, not that I drew it to scale, but because those turned out to be the same, that's exactly the case. And so that was the same answer I got here. Now, it's not going to always be so nice where you can just say, oh, look at that, I can just straighten it out. Quite often it's a really crazy crazy integral. This is not anywhere near as nice. There's no way you can just say, hey, I know what this looks like if I straighten it. And we have to just do the integral. Let's do another one where maybe that's the case. I want to do this curve. R of t is 2t, t squared, 1/3 t cubed. This is between 0 and 1. I'm just pulling this one as one of the examples out of, I think it's problem number 2 or something in the homework assignment. But linear in the x direction, quadratic in the y direction, cubic in the z direction. Okay. The derivative is 2t t squared. The length of the derivative vector is the square root of 4 plus 4t squared plus t to the 4th power when you square each of those. And so the arc length is going to be the integral from 0 to 1 of the square root of 4 plus 4t squared plus t to the 4th dt. Now, when I write problems for quizzes and exams, I'm not really very careful about what functions I grab. to make my vector functions with. Textbooks have a tendency to be very careful, and so that they can get integrals that you can actually do by hand. This one, maybe not immediately obvious, but the stuff under the square root factors there. This is the square root of 2 plus t squared squared. So if I take the square root of 2 plus t squared, I just get 2 plus t squared. So this is the integral of 2 plus t squared dt. Now, generally, this integral is difficult to do, and quite often impossible to do by hand, but it's a definite integral, and you can just type it into your calculator. You know, even a measly TI-82 can do a definite integral. So for myself, I don't mind getting this integral set up and then just letting the calculator do it, but because it's pretty easy here, I'll finish this one by hand. All right, so we've got, what is this? 2t plus t cubed over 3, evaluated between 0 and 1. So I've got 2 plus 1/3 minus 0. So 2 1/3. So what's that? 6 7/3. Okay. Now I do have one sort of reality check I can do here, in that just if I did the straight line from the starting point to the ending point. So, right, if I plug a r of 0, plug the 0 in, I've got, well, 0, 0, 0. So this starts at the origin, and when I plug a 1 in for the other endpoint of the interval I'm interested in, this would be 2, 1, 1/3. And if I look at the straight line distance between those two, that would just be, well, just be the length of r1 here. So, because I'm doing 2 minus 0, 1 minus 0, 1/3 minus 0, square each of those, add them up, take the square root. So that would be 4 plus 1 plus 1/9. So we're looking at the square root of 5 and 1/9. Is that 46 over 9? So it's the square root of 46 over the square root of 9, but the square root of 9 is 3. Comparing this, right, my answer was actually 7/3, and the straight line distance is the square root of 46 over 3. 7/3, if this should be the shortest distance between those 2 points. The curve probably takes longer. Is 7 bigger than the square root of 46? Actually, it is. 7 is the square root of 49. So, yeah, this is a little bit longer than going the straight line distance between the two of them. Okay. If this had turned out to be a smaller number than that, then it's like, maybe I did something wrong. But with this being a little bit bigger number, it's like, yeah, that's plausible. It's within the realm of possibility. And, well, that's the length of the curve.